Edexcel Core Pure, Calculus 3, Inverse Trigonometric Functions, Differentiating Arc Sin X. The inverse sine function. There are two main ways of writing the inverse sine function. There's the more formal arc sin x and the sine minus 1x notation, which you often find on a calculator. It's very important that we do not confuse the sine minus 1 notation with the reciprocal notation 1 over sine x. So 1 over sine x is not the same as talking about the sine minus 1 of x, or the inverse function. So we mustn't confuse it with the reciprocal. Just for consistency, throughout these presentations we're going to use the notation arc sin x to represent our inverse sine function. So now if we look at the graph of arc sin x, it has some important features. We can see the domain of the function goes from x is minus 1 up to x is 1. It's a one-to-one mapping in order for this inverse function to be defined, and the range of the function is from minus pi by 2 up to plus pi by 2. So we've got a very clearly defined range for this function. Another important point is to look at the gradient of this curve. The gradient of this curve is always going to be at least 0. It never has a negative gradient, no matter where you draw the tangent. So the gradient will be at least 0. Now we're going to consider differentiating arc sin x. And the way we do this is, instead of considering y equals arc sin x, we rearrange this into the more familiar x equals sine y. I'm now going to differentiate both sides with respect to x. So if I differentiate x with respect to x, we get 1. Differentiate sine y with respect to x, so this will be the implicit differentiation. So differentiate sine y is cos y times dy by dx because of the implicit nature of this derivative. If I rearrange this for dy by dx now, we get dy by dx is 1 over cos y, and we are going to take advantage of the identity cos squared y plus sine squared y is 1, which I can rearrange for cos y. So dy by dx is 1 over, and instead of using cos y, I'm going to use plus or minus the square root of 1 minus sine squared y. And there's a couple of important things to be aware of here. We saw on the previous slide that the gradient of arc sin x cannot be negative, so we don't need to include the negative square root, and we also have sine y defined at the top of the screen, so we can use that as well now. So we can say dy by dx is 1 over, we don't use the negative square root, the gradient must be at least 0, and sine y has previously been defined as x, so this becomes x squared. So we can see a bit more detail here, and just look at bringing out some of the key features that we will be using in future sessions. So we've taken this inverse trig function and we've rewritten it in terms of the trig function sine. Then we've differentiated both sides with respect to x, and once we get it rearranged for dy by dx, we've used the identity, so we know that cos y is plus or minus the square root of 1 minus sine squared y. We don't include the negative square root in our answer because we know the gradient can't be negative, and we also know that sine y is the same as x. So because the gradient cannot be negative, we end up with the derivative of arc sin x is 1 over the positive square root of 1 minus x squared. And we're going to be using this in future presentations. So now we have the derivative of dy by dx, we can just check one or two features in a bit more detail now. For example, when x equals 0, this gradient becomes 1. So we know that the gradient at the origin is 1. And if we look at the diagram, the gradient at any point on this inverse function other than the origin will be steeper than 1. So for example here, the gradient is definitely steeper than that of the line y equals x. So that means that along this inverse function, the gradient is in fact at least 1 all the way along. The only point where it equals 1 is when x equals 0. So at x equals 0 at the origin, the curve and the line have the same gradient of 1. So now we're going to make things a little bit more sophisticated, and we're going to look at the general derivative now, y equals arcsine x over a. So again, I'm going to rewrite this as x over a equals the trig function sine of y, and I'm going to differentiate with respect to x, both sides with respect to x. So if differentiate x over a, that will become 1 over a. Differentiate sine y, so this will be implicit, it will become cos y times dy by dx. Little bit of rearranging, dy by dx is 1 over a cos y. Again, we're going to use cos squared y plus sine squared y is 1. Rearrange for cos y, it's the cos y I'm going to use. To get dy by dx is 1 over, and there are potentially two square roots, a square root and cos of y, cos y is square root of 1 minus sine squared y. Again, we know we don't need to look at the negative square root because the gradient is going to be at least 1. And we also know that sine y has been defined as x over a. So this can be tidied up now to dy by dx is 1 over a times the positive square root of 1 minus x over a squared. And the last step is to bring this a inside the square root. So when I bring that a inside the square root, it will become an a squared. So we've got 1 times a squared at the beginning, and x over a squared multiplied by this a squared will just leave a negative x squared. So that is a very useful derivative of arcsine x over a. So just to run through a couple of those key points again, we rewrite the arcsine x over a in the much more familiar trig function sine y, differentiate both sides with respect to x, and rearrange for dy by dx. We only need to take the positive square root because we know the gradient is at least 1, and we can replace sine y with x over a. And you can put an extra step in here. So in this extra step, we've taken 1 minus x squared over a squared and put it over a common denominator before bringing the a back inside the square root as an a squared. So that is the derivative of arcsine x over a. So here we have the fairly standard derivative. If you differentiate arcsine x, you get 1 over root 1 minus x squared. But it's the more general derivative of arcsine x over a which is particularly useful. It's worth noting that if we take this more general case and let a equal 1, then this more general case will become the fairly standard derivative. So if you learn this more general case, you can always let a equal 1 if necessary. These results are going to be particularly useful later on when we start to look at integration of various new functions. In the next session we're going to be looking at differentiating of arc tan x.